This is example 2 from lecture 1.8, which covers projectile motion. Okay, this is a baseball problem. Sarah is our batter. Here's Sarah. She's at the plate. And she hits a baseball with an initial speed of 32 miles per hour at a 55-degree angle to the horizontal. So this ball has this V0 speed there, 32 meters per second, at a launch angle of 55 degrees. Meanwhile, Adam is out here playing center field, and he's going to attempt to catch the ball. And he's 85 meters, looks like almost straight out to center field. And he's then going to start running. This green arrow here shows that he's going to start running and try to catch the ball before it hits the ground, and then Sarah will be out. And we also know that the direction that the ball takes is 22 degrees from Adam's line of sight to home plate. So that gives us our geometry information. So the question is, what is the average speed that Adam must make, and what direction must he run in order to catch the ball at the same height from which it was struck? So since the launch height and the landing height, landing in the glove, is the same, then that means we can use the range equation that we've already developed. And then also we want to figure out the angle with respect to Adam's original line of sight to home plate. So I'm going to do this in blue. This is the angle that we're going to want to figure out that will describe the motion that Adam needs to run in. Okay. So first thing we want to do is calculate an average velocity. So we have a V average, and an average velocity is always some distance over time. And so it's going to be some distance that Adam needs to cover divided by time. And so I'm going to draw this line here in blue. This is the distance D that Adam needs to cover to catch the ball. And the time is going to be the time that the ball's in the air. And we're going to use the range equation to figure out R. R here is going to be the distance that the ball travels along the ground. And we can also use that to figure out the T. We're going to need R to figure out D, the distance that Adam needs to travel. We use law of cosines or law of sines to figure that out. Okay. So in order to get D and T, we need R and T. So let's use the range equation. The range equation tells us that, or one of the equations that we got in deriving the range equation was the time the ball's in the air. It's 2 V naught times the sine of theta naught divided by G. And I know all this information. We have a 2. My V naught was given as 32 meters per second. And then we have the sine of 55 degrees. Remember, the sine of 2 theta only shows up in the R equation, not in the T equation. So it's just the sine of 55 degrees. And when we divide by G, which is 9.81 meters per second squared. And if we calculate all that out and we're careful with our units, we get 5.34 seconds. That's the time that the ball's in the air. We can also then calculate R, the distance that the ball travels, V naught squared over G, now times the sine of 2 theta. That's our range equation. And we know all this information also. My V naught is 32 meters per second. We square that. We divide by G again, 9.81 meters per second squared. And then we multiply this by the sine of 2 theta, which is 2 times 55 degrees. That's 110 degrees. And once we work that out in our calculator, we get an R of 98.1 meters. All right, so we've got an R, and we've got a T. And we're on our way to calculating this V average. We know the T, but we don't know yet this D value, the distance that Adam needs to travel, but we know everything about almost everything else about this triangle. We know an angle of 22 degrees. We know the other two sides of the triangle are 85 meters and now 98.1 meters, so we can use the law of cosines and figure out this distance D. I'll do this on the next slide. Okay. So let me draw this triangle. This is my R here, 98.1 meters. This is the distance that Adam is from home plate. That's 85 meters. It's not really drawing the scale too well. And then this other side of the triangle, this is the distance that Adam needs to run in 5.34 seconds. And then we also know this angle here is 22 degrees. All right, so we're going to use the law of cosines to figure out D. So D squared would be the sum of the squares of the two sides, so 98.1 meters squared plus 85 meters squared minus twice the product of those two sides, 98.1 meters and 85 meters, and then multiplied by the cosine of the angle between those sides, which we were given as 22 degrees. So we work this out, solve for D squared and take the square root. We get a D of 37.2 meters. So now I can calculate my average velocity that Adam needs to run, which earlier I said was D over T. D now we know is 37.2 meters. Time is 5.34 seconds. So this works out to a speed, average velocity, or the magnitude of the average velocity is 7.0 meters per second. Okay, and then we're also asked to figure out what is this angle alpha? What is the angle that Adam needs to follow with respect to his line of sight to home plate? That's this line that's 85 meters. What is that angle alpha? That will now define Adam's direction, and we can define his velocity. So we can again use the law of cosines to figure out alpha. This time we're going to say that the angle, or the side opposite alpha, is 98.1 meters, so we're going to say 98.1 meters squared then is going to equal the sum of the squares of the other two sides, which is what we just figured, 37.2 meters, we square that, plus 85 meters, we square that, and then we subtract twice the product of those two, 37.2 meters and 85 meters. And then we need the cosine of this angle, and this is our unknown, cosine of alpha. So we solve this, we get a cosine of alpha of negative 0.1605 and an alpha of 99.2 degrees. So the combination of this angle and this magnitude, this speed, gives us our answer. That's how fast Adam has to run and at what angle, what direction he needs to run. So another question is, can Adam run that fast? Is it reasonable to think that Adam can run 7 meters per second? Well, I did a little bit of research, and I looked up Usain Bolt's world record time for the 100 meter. Right, so Usain Bolt ran 100 meters in 9.58 seconds. Right, and that's a world record, so Adam's not going to run that fast. This works out to 10.4 meters per second. So it's at least humanly possible to run 7 meters per second. Let's look at someone else. Let's look at UT defensive end Derek Barnett. Big guy, 6'3", 267 pounds. I'm guessing Adam can probably run faster than Derek. So I discovered that Derek can run the 40-yard dash. That's how they do this in football, 40-yard dash in 5.07 seconds. And if you convert the yards to meters, this works out to 7.5 meters per second. So I think Adam can cover the 37 meters, which is probably close to 40 yards, in 5.34 seconds if it takes Derek just a little bit more than 5 seconds. So okay, that's it for this example.